Cool. Welcome, everyone. Let me share my screen. This is Deep Learning Adventures, a fun and engaging community where we talk about data science and deep learning projects and really support each other in whatever projects we're working on. My name is George. I'm joined by great friends today around the world, around the country, especially by my great friends and colleagues, Robert and David, who are my co-organizers. Today, Robert and Alexandra are going to lead a session on feature engineering, which is our latest Kaggle course. But before we go there, just an overview. If you're joining us for the first time, welcome. If you're joining us from LinkedIn or YouTube, again, warm welcome. I want to make sure to welcome. You can find us on Meetup if you search for Deep Learning Adventures. Right now, we are wrapping up this Kaggle Mini Course adventure. We have about 3 more sessions coming up, as you can see here, on feature engineering, on reinforcement learning, and another one hosted by Robert on follow-up on one of the sessions he did with his Pedals to the Metal Cool event. All our sessions are recorded, and I'll post a link in the chats soon. As you can see, we've been pretty busy with basic machine learning and data visualization concepts to intro to deep learning and NLP, some SQL, some micro challenges with using different optimization techniques. And then we took a deeper dive on computer vision, some Kaggle competitions here. The latest one we've done is a fun interview with Kaggle data scientists Dan, Rachel, and Ryan. Then we actually deployed our own models on our phones. And last time, Robert gave us an overview of his fun SMS project. Today, we'll talk a little bit about feature engineering and what that entails. This is a new course for all of us who've been taking the Kaggle Mini Courses. Ryan mentioned in an interview with him that it was recently released. It covers a little bit of unsupervised learning techniques that we haven't seen yet on Kaggle Mini Courses, so it was really good to see that cover as well. It has a bonus lesson as well, which you can practice your feature engineering skills on it. Cool. I'll stop sharing. Again, welcome everyone. I'll enable screen share and I'll hand it over to Alexandra.
Hello, everyone. So I'm going to share my screen and we'll go through the first 2 sections of the feature engineering course. So you go to kaggle.com, you go to their courses, you'll find the feature engineering course down here. And so first 2 lessons. The first one just gives an introduction to what is feature engineering. And so brief course overview. So they teach a couple different things. So they show how to determine which features are most important using mutual information, and that's what I'll be talking about in the next module. And then Robert will be talking about the next few items. So how to invent new features, encoding features, segmenting features, and using principal component analysis. So let's get started. So what are some of the goals of feature engineering? So the primary goal is to make the data better suited to the problem that you're given. So oftentimes a model might be able to extract some information about the task that you're trying to learn given your data, but there might be some ways of looking at the data that the model can't directly perceive. So they give some nice visualizations of why feature engineering might be useful. So oftentimes you might have some data and there's some relationship, say, between your target variable. Say you want to predict the price of a house, and you have information about the length of one side of the land. So if you look at the scatter plot here, you see that there is a relationship and it's pretty tight. It's not linear because in the straight line, you see a straight line, the data doesn't quite fit it. It's some nonlinear shape. So if you fit a linear model, say you're using linear regression to predict price given length, your linear model will do okay, but it won't be great. Because there's some information about length and price or some information about its relationship that this linear model cannot capture. So this is where feature engineering comes in. What if we transform length and we just square it? We multiply length by itself, we get area, and this new feature area actually has a linear relationship between price. So we don't have new data, we just transform the feature so that the model is able to capture this relationship between, I guess, length and price that was there all along. And so this is a pretty common step in machine learning. It's a common step before you might train a model. So I think this is a nice illustration of like why we're trying to do feature engineering. So they give another example using concrete formation. So basically this data set contains a variety of different like aspects of the concrete. So concrete is a mixture of various things, and has different types of concrete have different compressive strengths. And so this data set shows different concretes and their components and the resulting compressive strength. And so here we see an example of feature engineering to help predict that compressive strength. So they approach this problem by building a baseline model to predict what is the compressive strength. So they just use a simple random forest regressor. They predict it with the given data. And they don't do any feature engineering. I don't think they scale the data either. And they just get the cross-validated score, which is 8. Now, they point out that one feature that you can create is creating ratios of ingredients in the concrete. So they create a couple of ratios between these different concrete ingredients. So this FC ratio is the ratio between fine aggregate and coarse aggregate. I'm not sure what these are, but they are ingredients. And they also create this other ratio. They aggregate the ratio as like a percentage of cement. And they look at the water cement ratio. The point is that they create some new features, say taking ratios of each other, and then they pass this new data set with these added features that are synthetic that we've engineered into the model, and our model score is lower. So before it was 8, and now it is under 8. So here we have found a way to help the model find more signal in the data about the target feature that we're trying to predict, compressive strength. Yeah, so I think that's a nice motivation for feature engineering and nice way of showing like the power that it can provide to your model. So the next lesson is about mutual information. So the motivation for looking at this is oftentimes with a new data set, there might be a lot of features. So it's common to get a data set with hundreds of features or thousands of features. And then a common first question is, where do you start? And so mutual information is a way of ranking the utility of all the features in your data set. And they rank it by measuring like the association and strength of association between a given feature and the target. And then you can use this measure to select a subset of features rather than using the entire feature set given. And it can show you that, hey, maybe one feature has no relationship. It's completely statistically independent of the target variable, in which case you now know that and you can discard it. So what is mutual information? It is a metric that can measure or describe relationships in terms of uncertainty. So it's kind of like correlation in that it measures the relationship between two quantities, but it's not, it doesn't measure linear relationships like correlation. It can detect any kind of relationship. It's so their definition of mutual information is it measures the extent to which knowledge about one quantity reduces uncertainty about the other. So if you know about one quantity, you have more confidence in knowing what the target is. So just, I'm going to give a visual to help you visualize what this does. So mutual information would tell you that there's a relationship between the sales price and the exterior quality of this housing data set. So basically what we see is if we know the exterior quality of a house, we know that its sales price range will fall within different bands, and the sales price range will differ depending on the exterior quality. And so because we know the exterior quality, we have less uncertainty about the sale price. We have more certainty about where the sales price might fall or what that price range would be. And they say something along those lines in the text here. They make a note that this measure of uncertainty is known as entropy. So basically, like how many observations do you need to see in order to be able to describe that data on average? So they talk about interpreting mutual information scores, which is pretty important. So mutual information can range between 0 and anything. There's no upper bound, but they give a nice heuristic. So they say that a mutual information score above 2 is uncommon, and it's a logarithmic quantity, so it increases very slowly. So knowing this, like if I see a mutual information score of 0, I know there's no relationship. If I see a mutual information around 2, I know that's a very, very strong relationship. Now, they have this plot that, so they have this plot that shows the relationship between, they show how mutual information values can correspond to features and the degree that the association, the degree that a feature might be associated with the target. So here we have our target, we have our feature, and it increases with, and here are the mutual information scores. So the mutual information increases as the dependence between the feature and the target gets tighter. This plot here shows that mutual information can capture any kind of association, not just linear correlation. So this is helpful. So, I mean, you could look at the correlation between a data set and it might have a low correlation, but the two variables might have high mutual information. And so they have some key points about things you might want to keep in mind when you apply mutual information. So it can help you understand like how useful a feature might be as a predictor of your target. But I think that one of the important things to note is that mutual information cannot detect interactions between features. It's univariate. So if like one feature alone isn't that useful, but it has a lot of information when it's, you know, taken in consideration with the second feature, mutual information won't tell you that. So if there's interaction effects going on, this metric won't tell you that. And they also note that how useful a feature actually is in your model also depends on the model you use it with. So if it's, say, you're looking at a quadratic relationship between the feature and the target, your OLS model, your linear regression model, might not be able to find it as useful as another model might be able to. So they give an example data set using an automobiles data set. So they have various features about different cars sold in 1985 and the sale price of that car. And they use this to show how you can actually use mutual information to evaluate how useful features are in predicting the car price. We note that you can do this for both continuous features and categorical features. So to do this, they first take all of the categorical variables and factorize them. In the factorize function, basically just label encodes the variables. And this was discussed in a previous Kaggle course. And the label encoding basically turns it into turns the category into an integer value. So then the next section is they show how you can actually make your mutual information scores. So scikit-learn has a mutual information regression function that can do this for you. They also have one for classification tasks. So if your target is a number, use regression. If your target is a category, use classification. And then you simply pass like your X. So this is going to be your data frame of all of your potential predictors, and your Y, your target. You just pass it in to your mutual information regression, and you tell it which features are discrete. And these were determined above. If the data type is an object, it's discrete. It converts it into a series and then sort. So this is the output. So for the automobiles data set, the most significant feature to predict the price per mutual information was curb weight. And so the mutual information score was 1.5. Before we said that a score of 2 is very uncommon. The score of 0 means there's no relationship at all. So a score of 1.5 for curb weight is very, very high. A score of 0.9 is also pretty high. And as you see, the mutual information scores decrease. The fuel type is pretty close to 0, and so you could say that the fuel type of a car in 1985 had very little bearing on the ultimate sales price. They also plot out the scores, and so you can visualize the scores in this way as well. And they highlight that the data visualization is a nice way to take a look at the utility of different features. And sometimes it's just easier to see the scale and relative scale of things via visualization. So here they plot out the relationship between the curb weight and price. And remember, curb weight is the feature that had a mutual information score of 1.5. So very high relationship. And you see the strong correlation as well. They also plot out the relationship between price and fuel type, which had the lowest mutual information score. But one thing they highlight is that in the plot, you see that if you plot out price versus horsepower, and then you show the difference between fuel type, the two types of fuel, so gas and diesel, you see that the lines aren't parallel, they're not the same. And so they're pointing out that fuel type alone has a low mutual information. It doesn't have much pertinence on price, but fuel type and horsepower taken together actually do have information together. So there is some interaction between fuel type and horsepower that gives information about price. And so this is what I was talking about earlier with regard to the interaction effects. Mutual information can't tell you that, but you might be able to detect those interactions in other ways. And they have it in the tutorial that I'll go through next. I actually explore trying to detect some of these interactions with mutual information, and I think it's possible, and I'll show you how in the exercise.
Before we go there, questions?
Yes, any questions?
So there were some questions regarding pairwise interactions. I mean, you mentioned that mutual information cannot detect that or cannot help us.
Yeah. So that's a good question. So just to know, I can't see the chat. What you see is exactly what I see. So you'll have to tell me.
Absolutely, yeah.
So the data set in this exercise is the Ames house price data sets. So this is basically a data set that tells you the relationship between different aspects of a house and its sales price. And I'm just gonna I'll go through the notebook to give clarity on the data set, and then I'll show you what I was talking about with regard to interaction effects. So here, I plotted out a couple of the variables in the data set. The sales price is on the Y, and the variable itself is on the X-axis. So here we have year built, and we see there's this definite relationship between the price and the year built. Of course, newer houses are more desirable, so you'd be willing to pay more money. we see the month in which the house was sold. There's not really any relationship here between month sold and sales price. And then last, the screen porch variable. I believe this is like maybe the square footage of a screen porch. But the point is that most of the observations have no screen porch. And so there's only a few observations where there is a screen porch. So here we plot out the mutual information of the variables. And so there's a lot of variables. So here we're only plotting out the top 20. And I'm going to jump to the bar plot. And so we see that the most important features with regard to the sales price of a house are the overall quality of the house, the neighborhood, the living area, and the year built. So these, of course, are pretty pertinent to buying a home. These are things that are pretty important. There's other important features are around like the quality of the house and the bathrooms. So that all makes a lot of sense. So that's a good check. And then the next plot, we're looking at the features that have the lowest mutual information. And so I guess the ones that have the least mutual information between the variable and the price would be like the porch, the month sold, information about utilities, pool, maybe the street, miscellaneous stuff, heating. So all of this is less informative with regard towards the sales price of the house. Just for some sense of scale, the least informative features, these are the top, least informative by 20. They range from 0 to 0.2. The most informative features range from around 0.2 to 0.6. So these aren't as high as some of the data sets that we saw before, but I think it's nice to get a sense that this 0.6 number for mutual information is still informative. Let's see. And so one thing that they start looking at is this interaction effect. So they plot out the relationship between sales price and the building type. So yeah. And this plot, like you can clearly tell there's a big difference between the different types of buildings. So single family homes, there's the biggest range of prices, but also the most expensive houses are single family houses. The range, I guess like the price range for townhouses is a little smaller, but still bigger than the others. Townhouse E would probably be townhouse End, which is more desirable because you have one neighbor instead of two. And then the condos and duplexes have the narrowest sales price band, and their maximum sales price is still lower than everything else. So the point is there's a clear relationship between the building type and the sales price, but the mutual information is small. So the thing that they want to look at is whether or not building type has an interaction between one of these two features. So the first is the above ground living area and the other is the month sold. And they want to see if, so building type has lower mutual information. Is there another feature with which, if you combine them, there's a high amount of mutual information? So here we see the plot. We're plotting the ground living area against sales price, and then we're grouping the plots by building type. And so just at a quick glance, you can tell that the relationship between the ground living area and sales price varies based off the building type, and you can see that the variance is quite large. The slopes of these linear trend lines is different depending on your building type. We do the same thing, but we look at the months sold. There's not much of a relationship between the different types of buildings. Months sold also has a lower mutual information, so perhaps that's some of what's going on. And so if you just look at this, so this is where I look at the interaction effects. So they plot out interaction effects between features that might have lower mutual information and features that have higher mutual information. And what I wanted to see is, can we use mutual information to like replace this plotting? So if you're going through a data set by hand, and there's, say, 100 features, you could probably look for interaction effects like this. However, if you have 1,000 features, looking for interaction effects in this way might be quite cumbersome. So what I did is I did something pretty simple. So we know that building type and ground living area have some interaction. We saw that in the plot. And so I factorized building type and just multiplied it by the ground living area. Super simple interaction. And I did the same thing for building type and months sold. And if you look at the mutual information scores, ground living area has a high mutual information. We knew that already. Building type has pretty low information, but the building type with ground living area has a much higher mutual information than just building type. And so I think this is an interaction effect that we were plotting. I think this might be the way to do it. The other interaction effect that we see here, the building type of month sold, it's the mutual information is just slightly bigger than just building type alone. So I would argue that this interaction effect is like, it's might be there, but it's very, very weak and probably not worth considering. And so then the rest of the notebook is about looking at, they suggest looking for more interactions. My goal was like, can we look at interactions more systematically? And I think this makes sense. Are there any questions about this exercise?
So there seems to be a common question in the chat about the difference between, people still don't quite understand the difference between mutual what's the name, the word again?
Mutual information.
Mutual information versus what you get with just like Pearson's correlation type.
Yeah, so the simplest difference is correlation looks at the linear relationship between two numeric features. Mutual information does not look at, it looks at relationships between two features, but it doesn't look for linear relationships. It looks for nonlinear relationships as well. And mutual information can also be applied to non-numeric categorical features. So we wouldn't have been able to do correlation between building type and price, for example, because building type is a category. So that's the simplest difference. Mutual information is also based on information theory. So here's one definition of it. So the implementation by scikit-learn, it relies on non-parametric methods based on entropy estimation from k nearest neighbors. So basically, if I were to summarize this, it's basically using estimations of entropy between the two variables in order to create this score. If I go back, to the original text material, they describe it as describing the relationship between two features in terms of uncertainty. So what you have a target feature, right? You want to predict sales price, or I guess the concrete compressive strength. And so if you add in this feature, how much can you reduce the uncertainty about your target given this new feature? So like if we don't know anything about sales price, if we want to know sales price. If we don't know anything about exterior quality of the house, the price could range from like almost 0 to like 700,000. But if we know that the exterior quality is only fair, we know that the sales price is probably going to be between near zero and be capped at around 200,000. And so here, because we know the exterior quality, our uncertainty around the sales price is greatly reduced. And that's basically what mutual information is measuring and telling us.
Awesome. Thank you, Alexander. There's a question regarding how do you pick two features and check if there's an interaction effect between them. Is there a systematic way to do it, or heuristic, or do you just pick maybe the one has the highest mutual information, one has the lowest, and just randomly try and pair them and see if there's an interaction effect?
They don't discuss that. What I was thinking of doing is I would just loop through everything. So some of it depends on your data set. So if you don't have too many features, you could brute force it and just like look at all pairs of variables and see if there's mutual information. It seems like what they do intuitively. So if, say we have 1,000 features, we probably don't want to brute force the approach. What we might want to do is, it seems like they pair a feature that has higher mutual information with a feature that has lower mutual information. So they were looking at this ground living area, and they were pairing it with, as we saw, I think the house type. I don't see that here in the bottom, but they paired something with high with something with like lower. So you could probably do something like, you could like take the top 20 and see if there's any interaction effects with the middle, I don't know how many features are, the middle 40. And then we probably want to ignore anything with a very low mutual information score. So like if the mutual information score is 0, we can definitely ignore it. If it's pretty low, or if it's in the bottom, we can also just ignore it. And so you could do some heuristics like that. So I guess like the heuristic that I'm describing is a way of like selecting pairs in a smarter way. So we probably don't care about looking for interaction effects between the top 20 because they all have, you know, high mutual information. So we know to keep them. But the question is, do we keep the next 20? Is the mutual information high enough if there's a interaction effect with another feature? So they don't discuss that, but those are my thoughts on heuristics on mining mutual information. I hope that helps.
Yeah, that's good as well. Anybody has any other questions? Feel free to unmute yourself. There's a lot of questions in the chat. I think Robert and David try to answer, and other colleagues as well, most of them. If you have any questions, now is a good time to unmute yourself and post them. Maybe it'll be easier than over chat.
Let's see. The question about, so there's a question about whether a feature was log transformed. I don't think so. Yeah, I think that's probably one of the weaknesses of the example analysis that they give, is there's no feature engineering either. I think it's just a feature selection task. I guess the challenge there, so I guess my bias that the perspective and bias that I'm thinking of is if I want to like do all of this automatically, how would I do that systematically? I don't think that's the drive, but yeah, I think that's a good point. Like if a feature should be log transformed, you should probably do that first. So I guess the approach depends on like how much domain knowledge you have.
And there are some other techniques we'll explore soon where scale is really important and you need to standardize your data, as we'll see soon. Yeah, so maybe you might want to look at mutual information after some sort of data standardization. Yeah. Cool. Thank you, Alexandra. That was great. Appreciate it. Awesome. We'll hand it over to Robert. The floor is yours, Robert.
Can you see my screen?
Yes.
Hey, we.
And I assume you can hear me as well.
Yes,
Now, which of these notebooks do I actually want to be on right now?
not the last one.
So we've finished the first two sections of the feature engineering course here, and we're going to move into the third section, which is called creating features. And this section is a bit of a hodgepodge of different techniques. We're also going to look at a variety of data sets here. We get the traffic crashes, we get automobiles, concrete formulations, and customer lifetime value all in the same notebook. Before we go any further, let me interrupt myself. Since I noticed so much traffic in the chat earlier, I would like to ask someone to monitor that, and if I need to be interrupted with questions, please direct them to my attention. I'm not going to be able to monitor the chat while running down through this notebook.
Don't worry.
Just let me know if there's something that's that we need to.
I would say let's take questions in the end of each notebook or each section. Let's do that. So I'll monitor the chat for you, and David as well.
Sounds good. So the blue boxes on these notebooks sometimes have the bottom line information that really summarizes everything you need to know at a high level from each of these tutorials. This one here, the main message is get some domain knowledge, understand your data set. Anything that you can bring to the data set beyond what is in the data itself could be very helpful in informing you what should be done to engineer better features. So they talk about domain knowledge here, research on real estate, Wikipedia, journal articles. But really oftentimes your best feature engineering is something that you know from first principles or just being familiar with your domain area. So we're going to start with a section here on mathematical transforms. And the idea of this is that sometimes interactions between various features can be expressed with very simple math functions that really capture the essence of the relationship and make it much easier for your model to learn the relationship than it would without you explicitly including this. So the very simplest example of a mathematical transform is what we've already briefly discussed in the chat. Things like a log transform, a univariate single transformation of a given feature. The simplest type of transformation you can imagine like that might be, if you think back to first experience with linear regression, usually the very first thing that they do to introduce nonlinear models is to create a polynomial regression where you'll just take a feature from your linear model and square it or cube it or something, and now all of a sudden you can fit a linear model, and you can fit a linear model to the result, but it's nonlinear in the original space. So mathematical transforms can be applied to multiple features at once as well. Here we're assuming that we know that there's some relationship between stroke ratio and bore in automobiles, and that will be most predictive of, I don't even remember what it is we're predicting in the automobile data set.
Price.
Is it price?
I think so. Of the car.
Yeah, it's price.
Okay.
It's the 1985 automobile data set from the other notebook. So
yes,
it's price.
Yeah. So simple interactions between parameters like that you can compute. They also show that you might want to do nonlinear transformations on a single parameter, such as the log transform we discussed previously. There's a very simple way to estimate what type of nonlinear transformation might be most useful for a given variable, and that is the Box-Cox transformation. And you can look that up on tutorials or online references. There's a lot of information on that, but it boils down to either a polynomial transformation or a logarithmic transformation, depending upon the shape of the data that you're looking at. For tree-based models, like we'll be using some of these univariate transformations, like a box Cox, aren't going to have a great deal of effect. They could change things on the margins regarding generalization capability, but they can be especially useful when combining features. So we have another section here on counts. And the idea here is that you may have a variety of features in your data set that encode some information, and maybe the most important predictor that you could get out of them is the number of trues across a variety of columns. So we have the data set here on traffic collisions. We have a variety of roadway features, amenity, bump, crossing, give way, all these different features. Each of them is a Boolean variable in the original data set. And the idea is that perhaps a useful predictor of the incident rate might be the sum of the number of these features. It's a kind of an oversimplification, but it could be a useful place to start. Certainly we wouldn't expect every one of these features to have identical impacts on the likelihood of a traffic crash, but each of these could be factors in any given instance. So it's just an illustration of how one can combine Boolean features into a single predictor that may be more useful.
And can I just clarify that we're looking at different data sets with different targets and applying different techniques? So if it sounds confusing, we had a car automobiles, this is crash accidents, we're trying to predict if an accident happened or not. Next, we're going to concrete. They're completely independent, just different techniques applied on different data sets.
Correct. This notebook uses 4 different data sets. I think each subsection takes an example from a different one.
Awesome.
And none of them are the housing prices data set that we'll be using in the exercises. So the second example here is another thing regarding counts, but now we're talking about how we can create Boolean variables from variables that are originally categorical or numeric. So here we have the concrete data set, and we have a variety of substances that could go into formulating a mixture of concrete. And the person doing the feature engineering is hypothesizing that maybe the number of components is an important predictor of the compressive strength of the concrete, more so than the magnitude of material in each of the components. So by using this .gt greater than 0, you are basically just summing how many components there are that are greater than 0 and writing that to a new column.
I have to say, working with data, that's a very useful feature because you can also change the threshold if you want.
Right. There's no limit on one's ability to invent new features. So the next section here we have building up and breaking down features. And the example here assumes that you have some strings and maybe there's some useful information within the strings, but it's not a simple categorical extraction. So the example they show here is about the area code. Maybe that contains some information about the location of the person in the data set. I'm going to assume that this particular area code doesn't contain much information because I don't think 999 corresponds to any location that I'm aware of. Perhaps I'm wrong. The string accessor, for those who are not familiar with it, is a super useful feature of Pandas, which ports over a lot of the string methods and syntax from base Python and vectorizes them so that they can be applied efficiently across a Pandas series or data frame. So you can take the customer data set here. This is even a fifth one that wasn't even mentioned at the, or no, I guess customer lifetime value. Customers of an insurance company. From the policy feature, you can use this string accessor and then just use a splitting on the space, expand true, and the result of that is that you can pull out different things from a single categorical variable. So for instance, here policy has, the original data set shows it as string space another string, but maybe it will be better for your model to separate them out so that you have one feature that describes the type and another feature that describes the level of insurance. And of course, if you had simple features originally, you might want to put them into a composed feature if you thought that there was some interaction in the combination. So you can go both directions on this. There are some other accessors in the Pandas library that are really useful to know about as well. One is the .dt, which is kind of the equivalent of .str. It allows you to do a lot of date-time functions vectorized. Not a focus of this course, but a super useful thing to be aware of for anybody working with date and times in your data sets. Group transforms are another transformation that we discuss here in this notebook. And this time the idea is that possibly the most useful aspect that you could capture about your categorical column is the mean of its value in some other field. So in this case, we're looking at states, and each state has a different average income. So imagine that maybe the most useful predictor of a certain target variable might be the difference in the customer's income from the average income in his or her community. An income which might be a median income in one part of the US may be very far from that in another part of the US, and so maybe the income on its own is not the best predictor, but showing it compared to the average income, maybe that's a more useful feature. So you can combine features in this way as well. Lots of other things you could do other than mean, max, median, etc. And you could also just count how many there are within each of these states. So you get to frequency encoding.
There's some jokes in the chat. There's some state that had 0 income. I think they're just missing data. Okay, so.
Yeah, either that or there's, where is it? Arizona. But see, it has average income 37,000.
I was going to say, with a non-zero mean.
I think that's a record then.
No,
right?
it's a head. It's a specific observation.
Yes,
We're
it's
looking
the
at 3
first
columns,
one.
so maybe it's a specific house or a specific, I don't know what data set this is.
Yeah, this would be like specific customers who have 0 income.
Hmm.
Yeah, just one record out of many.
But if the data set were just these 10 examples, then it would appear that people on the west coast of the US would be far better off moving north.
Let's do it. Oh.
Let's see, I think we've covered this all. Tips on creating features. So one thing that I mentioned really briefly at the top is that ratios in particular, they can be very difficult for models to learn. Depends a lot on the types of models. Neural networks, if you look at tree-based models in particular, you're likely to split on features individually. So ratios between features correspond to decision boundaries that will be angled through the space, not perpendicular to one of the axes. Neural networks similarly will be able to split based on linear combinations of parameters, but have a very difficult time learning ratios between them. So there was an exercise set, I believe this one, exercise 3. I'm going to move through this pretty quickly. I don't think there was anything super new in the exercise notebook here. So
The data set was different.
The data set's different, right? We have the Iowa home prices. Takes a while to get this thing started. I think these are just really simple examples of everything that we discussed in the original. So what we're going to be doing as we move through this course is we have a function here called score dataset, and we're going to be applying an XGBoost model, regressor model, to predict the prices of homes in Ames, Iowa, which is where the town where the University of Iowa is, 30 miles or so north of Des Moines, I think.
Didn't know that.
So what we have in here is we're going to do a cross-val score for the XGB model, and we're going to see how that changes as we experiment with these various feature engineering techniques. We're not going to play with anything about the model. That's not the function of this course. But the scoring method here, because cross-val score requires a score where the good is higher numbers, we use they've built in a method negative mean squared log error, which is kind of confusing, but the only reason it's made negative is because cross-val score requires that better models have higher numbers. So in order to then report something which is a little bit more intelligible after running cross-val score, we're just going to multiply by -1. So at the bottom of this notebook here, we got, after using a number of these techniques, we get a score of 0.13847. And we'll see that change a little bit throughout these succeeding notebooks. Are there questions at the moment?
Just a question, if you use neural network in this course. No, we use neural networks in other courses, but not in this course.
This course, we're just looking at the gradient boosted regressor.
Awesome.
All right, so let's move on to k-means clustering. So we're going to talk about unsupervised learning algorithms for the next couple of sections, and the difference between unsupervised and supervised is that now you are not making any use of the target value at all. The purpose of unsupervised learning is to summarize something about the portion of the data set which is the features, ignoring the target. Learn something about that. Maybe you're categorizing them, clustering them in some way, encapsulating something about the features, and that could be useful for your prediction task later down the road. So clustering here basically means putting data points into various groups. We start by discussing, I guess the phrase they have up here is birds of a feather flock together, so to speak. And that is trying to figure out which birds are in the same feather, each of these clusters. So we have two visualizations of clustering here, and these visualizations are on a single feature clustering. So all you can do here is you have features along a real line. The Y component here is just meaningless noise added so that you can see them. And we have three different clumps of homes based on when they were built. These are the oldest homes, the ones that are medium aged, and the newest homes over here. And it is possible that clustering in this way could be useful because you'll find that homes in different groups, maybe different models will fit each group better. So you can also do this with multiple features simultaneously, and that's where this method can become really powerful. So we'll see, again, this is just a two-dimensional visualization now, two-dimensional clustering, and we're looking at the houses in Ames, Iowa, and we are visualizing them by latitude and longitude. So it's just like looking at a map. And the clustering algorithm here is trying to choose clusters that have a small distance between homes within the cluster compared to the distance of homes between different clusters. So what we can see here is that this data set actually shows a variety of clusters, mainly because there are zoning and other things in US towns, and there's large areas where there just aren't any homes. So just for your reference, this empty block in the middle here is actually where the Iowa State University is. The campus here is in the middle. And the downtown is down around here. There's some, I don't remember what all is in here. Commercial district maybe. A little neighborhood of homes down here. And this is also university property where the agricultural research is done. Otherwise, you've got clusters of homes, and I think this is just out of town completely up this direction. So what they mentioned before, I don't want to forget this link right here, which is actually really cool. And that goes over here to scikit-learn feature discretization. A bit of a sidebar on this one, and maybe I should amend that. I don't know how cool this visualization would be for someone who is red-green colorblind. It looks like it might be a challenge. Maybe I'm wrong on that. But otherwise, I think there's some interesting lessons to learn in this one. So we're looking at 3 different data sets here and playing with feature discretization and the effect that might have when we look at individual unit, a single feature at a time. So we have 3 different data sets here. One is basically close to being linearly separable. We have the half moons data set here where there's kind of one class is clustered around this way, another class is this way. And we have this one which is really separated radially. And the first task here is to fit a linear model. And not surprisingly, we get pretty good accuracy when you fit the linear model on the linearly separable data set, 0.98, linear support vector classifier, and a logistic regression model. And when we do the moons, doesn't do too badly because you can see where the lines would be drawn there. And the radial one is kind of random, and the classification accuracy shows as much. When we do feature discretization in a single dimension, it's very interesting that this hurts the linear model because no longer is it able to split along the correct direction. It's now forced to make these splits in along a single feature at a time. So it's not able to find the ideal decision boundaries. However, in the other 2 cases, it does somewhat better. It does a little bit better in the moons case. Well, actually, the logistic regression, not so much. The support vector classifier is able to learn a little bit more of what's going on up in here. The radial data set, it's much better. With these linear splits here, it's able to, or with these single feature splits, it's able to learn that middle section is something different. And then just playing with nonlinear classifiers, but interestingly they chose a gradient boosting classifier here, which is still forced to exhibit that same single feature at a time decision boundary, but now it's able to do them in a little bit more complex way. No longer is one decision boundary going to be across the entire data set. So here you do somewhat better on the Moons data set. You do a lot better with the support vector classifier. And the support vector classifier actually does better, pretty much dominates the gradient boosting classifier for this data set, which is not especially surprising, I guess, because this is the type of regime in which the support vector method would work well. Very small data set with nonlinear interactions.
Question, is SVC the same as SVM, support vector machine?
Yes, I think it's just SVC because that's what scikit-learn calls it, and it's a classifier as opposed to a regressor.
So I have a clarification. I think what this plot is showing is, so you have linear classifiers, they do not that great. You have feature discretization in linear classifiers, and then you have like high complexity nonlinear classifiers without discretizing features, I believe. And I think the point is that the feature discretization can make the linear classifiers roughly just as good as the complex nonlinear classifiers, if I'm not wrong. That's the takeaway I'm seeing. The exact ranking will vary based on data set, I think. So like if you need, I guess maybe one application is if you want to use a simpler model because it's more interpretable, then feature discretization could help get you there. So you could like do the K-bins discretizer, and then you have this logistic regression, and then you can like explain your model a little bit better.
Yeah, that's an excellent point, and it's really borne out by that second row there, where the feature discretization plus the linear classifiers does better than the nonlinear ones.
Cool. Thank you for this branch, Robert. It's very interesting.
So I thought that was an interesting link. You can get to it from this link here on the original page. Let's see, what are we doing now? This one now, we're going to go back to this original year built clustering. We have homes built, and we're doing 3 clusters over the year built. And they just show an example that clustering and building a linear model can improve the classification performance. And this is, similar to what was happening on when we discussed just now on the feature discretization part, that once you break a feature into a few different clusters, now you can treat each cluster differently and fit a different model on each one effectively. So lots of different clustering algorithms. We're not going to go into the algorithm too much, but k-means is probably the most prominent clustering algorithm in use. It's pretty intuitive and it's easy to apply, as they say. The most important things to know about k-means from a high level is, first of all, the k is how many centroids there are in the results, and you need to know that the k is something that is user specified. It's not something that comes out of your model. It's something you have to choose before you even run this algorithm. So one thing that people often do is experiment and try different k's and see which one gets the best looking results. You might do that with visualizations if you have a fairly small, low dimensional data set like this one, or in a very high dimensional data set, it might not be practical to visualize, but there are a number of numerical metrics that one can compute to estimate the quality of your clustering. So this visualization here that we're looking at for the lat long, I think this is, once again, we're looking at Iowa homes, and this is actually the same clustering we saw above. And here we have our centroids. So there's 6 centroids. We chose k equals 6. The other really important thing to know is that this is a non-deterministic algorithm, and that you can run it multiple times and get different results. So it can be very useful to try, set it to run 10, 20 times, see that you're getting somewhat consistent results before you choose a final clustering. Make sure that the one that you're getting is reasonable. It's possible that you could initialize your centroids in a way that lead you to a bad result, but if you do it enough times, you'll find a reasonable solution usually. So this goes into the algorithm here a bit. We'll skip that. Just talks about what I think we just said about choosing the number of clusters k. And then we have a visualization here at the bottom on California housing prices. And we have 3 features we're looking at: latitude, longitude, and median income. And this doesn't really look like an income. I believe it's in tens of thousands of dollars, I think. So we're looking at different, I don't remember what the regions are either. This may be zip codes, or maybe it's census blocks, something like that. Now, one thing that they do point out, which is really important to know, is that k-means clustering is using a distance metric, typically Euclidean distance, in whatever feature space you give it. So it can be very important to rescale or normalize the data in advance. Having said that, this example chooses not to, because it turns out that these features begin on roughly the same scale, in spite of, maybe that's why we're using tens of thousands of dollars here. Anyway, they were close enough to run this example. So we're looking at the result of a cluster fit. It's pretty simple. Fit predict will give you the fit and then choose which cluster each data point goes into. So that could be added as a new column, and then it'll be a categorical with these 6 clusters. Or you could run a fit transform, which actually gives you the distances. I think they do that in the exercise. And now we get a visualization of the clusters. So remember that our 3 variables we were looking at were latitude, longitude, and median income. So anything you see on this chart that doesn't look spatially related is likely to be about income. And so I think if one is familiar with California and looks at this chart, it looks like, it's interesting, you've got 3 kind of big geographic regions, right? There's north, middle, and south from the looks of this clustering map anyway. There's like Northern California, Central California, and Southern California, which are represented by the purple, red, and blue dots respectively. And then there's some other clusters that essentially capture the high-income areas of California separately. So the orange ones may be the high-income parts of Northern California. The green ones are higher income parts of Southern California. And if you look very closely, you'll see just a handful of dots with this brown one, which will be clarified by the next chart here. And yes, that's because those are super high income or super high house value zip codes. So that might be, I don't know, it looks like ones along the beach here. Someone more familiar with California than I may be able to identify these particular neighborhoods. But
So I don't mean to interrupt, but it looks like the orange cluster looks like San Francisco, Berkeley, and the green looks like LA.
That's correct.
Yeah, so I think it's interesting that it's clustering like those like high density, high cost cities, and then everything in between.
And to make it more complicated, within green, there's a brown as well, and blue. Like, I don't know if you can zoom in, but yeah, I can see the brown in 118.34 coordinates. Plus,
Yeah, it's like right on top.
yeah. So maybe that's the high rises or the more expensive ones. I'm not sure.
Yeah,
Beverly Hills, that sort of thing.
that's what I was thinking.
Irvine,
Maybe Beverly
Newport,
Malibu?
Malibu.
Malibu, maybe this one right here. I think this one may be Beverly Hills. This one may be like Palos Verdes or somewhere.
Newport, I think, right?
No, Newport's a little farther south.
Right?
It's probably Venice Beach or something.
Oh, that could be, yeah.
Oh, you California kids.
Where dog houses cost more than cars.
The dogs too.
All right.
So I don't know what the scale is here for the house values. This may be in hundreds of thousands. No, it's probably millions. I have no idea. Seems too high to be millions, too small to be 100,000. I suppose one could find that in the data dictionary that's associated with the California set. We'll move into the exercise for this one, the clustering with k-means. This notebook has a couple of interesting questions in it. Run all. So one of the first questions is, we're talking about scaling features before running k-means clustering, and we are given some hypotheticals. Would you scale features if we're talking about latitude and longitude of cities? Would you choose to scale features if you're talking about lot area and living area? Or would you choose to scale features when you're talking about number of doors and horsepower of a car? And I wrote my own answers here. But the idea is that for features that are definitely not related to each other dimensionally, you usually would want to scale them, like number of doors and horsepower of a car. They're going to be on completely different scales, and if you want to make any reasonable distance metric between them, you definitely want to rescale them. Talking about lot area and living area, these are maybe on the same scale, but maybe they're capturing different components of the value of a home, so maybe you'll want to rescale. You also may be looking at properties with really large lot areas and small living areas, or the opposite, depending on what neighborhoods you're looking in. So either one could be reasonable. I think I chose to rescale this one for the exercise just because it looked like the lot areas were 10 times the standard deviation of the living areas. So I thought that was a good enough reason to rescale. For the lat long one, I think that this could be a bit complicated. Like if you really want a distance measure, then maybe you'll multiply longitude by the cosine of the latitude, because otherwise you're not really on the same scale. But I guess that's technically a rescale, but you really don't want to scale this one based on spread within your data set. Suppose you have a kind of a long, thin area that you're looking at, then you could misrepresent distance badly by rescaling based on your data. So let's see.
I have a question.
Oh yes, good.
Well, yeah, so how is feature engineering for latitude and longitude handled other than the clustering? Or do you just have your own recommendation?
How is feature engineering for latitude and longitude handled other than the clustering?
Yeah, like what might you do with those features? Like if you were to say combine them into one feature that like tells you the point location or like something like that. Is that something you considered or was discussed in the notebook?
I will say it was not discussed in the notebook. I think that there could be certain prediction tasks in which you might want to convert those features to other scales or other features entirely. For instance, if you're looking at the data set of, or a data set of highways or traffic crashes or something, maybe you want to know at what distance marker you are on the highway when something occurs. So maybe converting it to a linear measure along the length of the highway is more useful than lat long. But the course doesn't go into anything other than that. We're really just looking at homes and distances between them, so there's no reason to go beyond what we've seen here for that.
Okay.
You also a lot of times are looking at how it maps to other data. So census tracts or things like that, right? And then once you have a census tract, you have a lot of other data available to you. So there may be ways to use it that way too.
That's true. You could encode it categorically, right, through a census tract. You might want to use GeoPandas or one of the tools that we learned in the geospatial course to do that effortlessly for you. Let's see. So this one was pretty interesting here. We did a k-means clustering on the Iowa home price data set that we had seen before, and I think I was just looking through trying to come up to my own conclusions on what each of these colors might represent. So we did a k-means clustering of 10 clusters on, I think it was just those 5 features. I don't remember how many features were involved, if it was just those ones. Yeah, it was just these 5 features. So you could come up with conclusions about what each color might represent. For instance, the cheapest properties here were likely to be the orange, the brown, and gray clusters, but the gray ones seem to be ones without a basement, and the orange ones tended to, what was that, have a second floor, while the other ones don't. So just little ways of categorizing these into groups of similar homes. And we ran score data set at the end of that clustering, and you get 0.14, which is actually worse than you had on the previous notebook with the hand-engineered features. Then we do cluster distance features, and to do that, you're just using the fit transform method, as I mentioned earlier, instead of fit predict. So now you're not using the cluster identifications, you're using the distance to the 10 centroids and running that through your XGB regressor. And so I wasn't terribly surprised. That one actually does worse yet. So, and that's the end of this section.
Awesome. Thank you, Robert.
So let's go to the principal components analysis. Were there questions we need to?
No. I don't see any. If there were any, we try to answer them in chat.
So principal components analysis, this is our next unsupervised clustering method. We talked about this in the chat at the very beginning of the meetup. So you're really just looking for which components or you're looking to cast your data into a new basis, which is dependent upon capturing as much of the variance in your data as you can in each successive component. So you can think of PCA as like finding whatever rotation matrix moves your data into this basis that maximizes its variance successively in each one. So technical note, it's very important to standardize your data before running PCA. And then we're going to look at an Abalone data set here. This is a sea creature. So what was interesting about this data set here, we see that the abalone have been measured with height and diameter. And you can see that the heights tend to correlate with the diameters. And in fact, it's not too surprising, right? You can think that these ones are just bigger than the ones down here. And then this perpendicular axis is capturing some kind of information about the shape of the abalone. So if it is this direction, I suppose it is a larger diameter than its height would predict, so it's maybe a little bit fatter, and the ones down here are a little bit skinnier. And they've called them the size and shape components accordingly. And the idea is that if you look at the size feature, that alone captures over 90% of the variation in the original data set. And this can be very helpful for analyzing your data set and or generating new features for a variety of reasons that they go on to discuss further down in this notebook. First of all, a little bit of terminology. What's the principal components, and the weights themselves are called loadings. But again, it's really just calculating whatever rotation matrix gives us the most capturing of the separation of the data in the early principal components. Principal components by definition are always orthogonal to each other as well. So in this one, we get 96% of the variance is explained straight in this first PC. And one thing that is very important to remember is this last thing they throw in at the very end. The amount of variance in a component does not necessarily correspond to how useful it is as a predictor for your target variable. So it is possible that your size may not have anything to do with whatever it is that you're trying to predict.
Robert, can you elaborate a little bit on that? What exactly that means? That size accounts for 96% of the variance between height and diameter.
Sure. So when we talk about variance here, I think we're talking about the distances in this two-dimensional coordinate system here. The variance in both height and diameter. And the reason we use variance is that it's pretty easy to define as a Euclidean distance squared metric. And if we know the height, then what we've done is similarly to the way we saw in the mutual information notebook. If we don't know the height, we know the diameter only to within, the standard deviation might be 2-ish. And if we do know the height, then we can bound it pretty tightly, and the standard deviation may be less than a half. So just knowing one variable is able to reduce the variance on the other one. And this is, and essentially you'll compute this the same way you'll compute an R² for an ordinary least squares linear regression or any kind of regression model.
Got it.
So this 96% here is related to the concept of R².
Mm-hmm. Cool, thank you.
So later in this notebook here, down here where it says PCA for feature engineering, we see a few examples of how it could be very useful for feature engineering. So the first thing we talk about is that just using it as a descriptive technique, you might get ideas for what other kinds of features to engineer. Looking at it, you might see from this plot here that maybe a ratio between height and diameter would be a useful feature. The second way is to simply use the components themselves as features. So you'll be using size and shape instead of height and diameter. In general, you won't be able to assign names to them quite so simply. You may have many, many dimensions, but this is a useful conceptual example to understand what's going on even just in 2 dimensions. So the first one they mention here is dimensionality reduction. And the idea here is that if you have a lot of dimensions, often you'll have a data set where some of them are just somewhat redundant. And PCA is just going to show you that you've got a number of dimensions that you can just drop since they contain little or no information. Another really useful one is anomaly detection. So if we go back up to our original figure here, imagine what we might see if we had, say, a point right here at height 2, diameter -2. And these have been standardized, which is why we have negative values. So this is definitely an anomaly as we look at this data set here. But if you looked at the original features individually, they wouldn't be, right? A height of 2 would fit right into the original data set. A diameter of -2 would fit right into the original data set. But once we express it in the coordinate system size and shape, then the size is reasonable, but now the shape is going to be, way down here or something.
Diameter
So that
of
will be
-2?
much more obvious as an outlier after conducting the PCA.
Something to
Diameter of
note.
-3?
Go ahead.
How can you have a diameter of -2?
The features have been standardized, so it's just 2 standard deviations less than the mean.
All right. There's z-scores.
Yeah.
So one note on anomaly detection. So I have actually used PCA for anomaly detection. So if you want to scale your data, you'll want to make sure you use like a robust scaler. So that way like your like scaled features are not like thrown off by any obvious outlier like you described. And then my other point is that PCA really is useful for anomaly detection. The way I've used it is I use it as like a compression technique, kind of like an autoencoder, but it's a linear, simple version of an autoencoder. So you extract like key components, and maybe I just extract 1 or 2. I basically then I like reconstruct the original data just using like 1 or 2 components instead of say 10. And then I look at that reconstruction error. And if that reconstruction error is high, then that might be an anomaly. And that's one way of like using PCA to find anomalies in say like a high dimensional data set.
Yeah, thank you for that example. That is a great example and shows the value of a technique like PCA. They give a couple of other examples here: noise reduction, in boosting signal to noise ratio. Decorrelation, this is also a kind of a lazy way to decorrelate your data. So if you want to fit a linear model and you want to make sure that you're not going to cause problems with features that are too correlated, you could run PCA on it, then get the top X principal components, and you probably have a pretty good algorithm and you know that they're all uncorrelated. So we talk about best practices here. I think we've talked about all of them. Numeric features only, sensitive to scale, you need to scale it, and we discussed outliers, but if you do find these large outliers, it can be useful to sometimes just remove them and then rerun PCA, because they can completely throw your averages off track since we're talking about L2 distances. And then we go into another look at the 1985 automobiles, trying to predict the prices. And this was a pretty interesting little sidebar here into this data set. We fit PCA on it. We see the principal components. This is actually what the values in the data set, like data point 0, data sample number 1, this is what it is now expressed in the new coordinates. So these two are identical for some reason. But after fitting, we end up having this matrix here. This is your rotation matrix of the principal component loadings. And you can get some intuition by looking at this. So what you can see here is that the first principal component is increases with engine size, horsepower, and curb weight, and decreases with highway miles per gallon. So you might try to think to yourself, what does that represent? And he talks about maybe it's a luxury versus economy axis. And that makes some sense, right? These three tend to mean larger vehicles, more powerful vehicles. Highway miles per gallon will go down with them. The highway miles per gallon going up tends to indicate economy vehicles. I don't know about, I've always thought that the word luxury tended to be more about the interior features, and so I would have maybe called it an economy axis or something, or anti-economy axis, since positive values are the least economical vehicles.
Or environmental versus non-environmental friendly axis.
Yeah, that could be it. And then I looked at principal component number 2, and this one's kind of tough. So goes up with highway miles per gallon, also goes up with engine size, but doesn't really vary too strongly on horsepower and curb weight. So the best I was able to come up with that one is, maybe it's some kind of like capturing how aerodynamic the vehicle is compared to its weight and the power of the engine, how efficient the engine is. I don't know. That one was tough. If anybody has any ideas, let us know.
Well, what's the explained variance ratio for each of the components? Because maybe the explained variance ratio of the second one is kind of low anyways, and so you probably shouldn't read too much into it.
You're right. The explained variance ratio we get to a little further down, and most of it's in principal component 1. But principal component 3 is a little bit more interpretable, I would say. Like horsepower up, curb weight down. So he goes into that down here, and he says this is kind of your sports car versus wagon axis.
Yes.
So, right. So as Alexandra just mentioned, most of the variance is explained in that first component, and then each successive component explains a little bit more of the variance. And based on the way that PCA is computed, that these will always be decreasing here.
The second one is interesting. I'm trying to figure out an example. It's not sports car versus not sports car. I think that's the third one.
Yeah.
That's interesting.
I couldn't really come up with anything too convincing on the second one. And he doesn't mention
probably a utility vehicle.
Utility vehicle?
Something in the data.
Like a truck?
Yeah, something that you use for a business. You want really high gas mileage, maybe a big engine to haul your stuff, but horsepower, it's not an actual puller. It's just like
Sure.
like a UPS truck.
Usually utility vehicles don't have good highway miles per gallon, do they? Because they're heavy.
Or maybe like a car rental, who knows? Utility.
Is there an electric vehicle or hybrid vehicle here?
I don't know. So he goes on and talks about principal component number 3, We do look at the mutual information scores as well, and not too much of a surprise. They're kind of in the same decreasing order as the principal components, which is often going to be a relationship you'll see. He goes on and talks about the horsepower versus curb weight, the principal component number 3. And you can see this when you sort by PC3, right? The top vehicles here are Porsche, and the bottom here, Toyota wagon.
Yeah, this is easier to interpret, yeah.
And yeah, just engineers a new feature based on that, just showing how this type of analysis might inspire you to create a new feature. So let's see, was there anything in this exercise that was needed? If there was.
So I just, before you go forward, I'll just point out one of the points kind of you're making indirectly is I always find principal component analysis hard to do interpretability of your model with, right? You're using models such as XGBoost or random forest that are very easily interpreted, but then you do PCA and you lose a lot of that. It makes it harder anyways. I don't know if anybody else has that same impression, but.
Yeah, that's why there's factor analysis, which applies a whole bunch of transformation matrices on top of the PCA to try to get it to where it is relevant to the people you're talking to. And there's a lot of them. At least in psychology, which is where my graduate degree is.
So here we're just applying PCA to the same housing price data set, and we're trying to interpret the component loadings that we saw. Here we're looking at garage area, year remodeled or an addition, I think, total basement square feet, and ground living area. And you can interpret a few of these components. I think the first component I identified as kind of a big versus small component, with a little bit of influence from the year as well. Whereas the second component was sort of perpendicular to that, and it's like big and old versus small and new. And then a couple of other axes, PC3 and 4. Let's see, the second one here, this one was where you get to play around with a number of hand-designed features. I tried a number of things that are mostly commented out now, but I did note my scores that I got. So the best score here was using this solution that Ryan put in the solution hint, the ground living area and basement square foot, just adding them together. That one lowered it to a score of 0.134. Otherwise, let's see. So I tried engineering a few features. In order to pass this exercise, you had to get below 0.14, so I just barely missed it on my first try here, adding a few extra variables. Garage area, total basement area, ground living area, summing up some areas. Tried a few other things. When I tried just the PCs, all you need is the first PC to get under 0.4. So those were useful, but this engineered feature down here was the best of those solutions that I tried up there. Oh, just looking at the principal components. Not too interesting. The first one has a higher variance, as you'd expect. There's a few outliers in each one, but nothing too far beyond that's shown here anyway. And some outlier detection. Now we aren't plotting anything here, but it was interesting when we sorted by the principal components. one could see that a couple of the same homes came up when they were sorted by multiple principal components. So any questions on the PCA that we haven't covered?
Some questions with correlation, covariance that Chris and Jay are chatting about, but nothing else.
All right, then I guess I'll move on to the target encoding notebook.
Last section, yeah.
Yep. So most of the features, most of the techniques that we've seen have been for numerical features. Now we're going to look at target encoding. So we've already talked about encoding, but we've been talking about some kind of a mean encoding of a particular feature. But now we're just going to encode the target, not a predictor, but the target itself. And that introduces a couple of challenges. You need to take some care to avoid leakage, as we'll see in this notebook, but primarily in the exercise, I think. So for this one, they show a very simple example where you might use a group by and aggregate. So maybe if you want to predict the price of an automobile, maybe just knowing its make and saying, well, whatever the mean price of an Audi is, or whatever the mean price of a BMW is, that's a pretty good guess for my model to start with. So that's what we are showing here. Pretty simple. You can do it for a binary target, and in that case it would be called bin counting. And let's see, I have the other names you might come across include likelihood encoding, impact encoding, and leave one out encoding. And somewhere I Googled some of these things and ran across a blog post that someone had put up on Toward Data Science, which is the most comprehensive treatment of like every possible target encoding you could imagine. I'll place that into the chat when I get a chance.
Sounds comprehensive.
I think my team was just looking at that same article.
Yeah, I think there was something like 15 different target encodings, all described in detail. It was pretty intense. So smoothing. So there's a couple of issues that you run into when you try to do an encoding like this. And if you imagine, so running something like this where you have, maybe there's a bunch of Audis in your data set, lots of data in a particular category, fine. But what if your data set only contains 1 or 2 BMWs? Or a very small number of Lamborghinis or some other car that just most people don't have. In that case, you could end up with some problems here, and there's a couple of different risks. First of all, you may need to impute from scratch, right, if you just don't have any and it's in your test set. But you'll also run into the issue of rare categories, and the statistics computed on a rare category may not be super accurate. So you have this problem of, well, if I'm looking for the statistics on Toyotas, that could be very accurate because many people drive Toyotas, and you look at the statistics on a much more specialty car, and that will be a less useful feature. So is there a way to capture this trade-off so that this feature is valued for something where we do have a lot of data and is valued lower for something where we don't? And so the idea is that we're going to add smoothing. And what we want to do is choose weights so that we multiply the in-category average by the weight, and then 1 minus the weight times the average of everything else, or the overall average. I don't think the in category is subtracted off there. In any case, it's a convex combination of these two numbers, the in category average and the overall numbers. So when we have a target for which the in-category average is a very useful feature, we're going to want to have a weight that is closer to 1. And if it's a very rare car, then maybe we want to keep the weight closer to 0 just to make sure that we're not overfitting it to the 1 or 2 values in our data set. So what they show here is that one way you can do this is use an M estimate, where N is the total number of times a category occurs in your data, and M is some hyperparameter that you can tune or just choose straight out and see how it works. So this plot shows a little bit about what that trade-off is. I sometimes think that it's useful to imagine the edge cases, right? So here we see M 0.2 and going up to M equals 0.4 or 4.0. But if you imagine what happens for M exactly equal to 0, well, it's still going to be 0 when the category count is 0. You have to impute there. But then it's going to jump up to 1 here. It's going to be noisy and it's going to overfit to that 1 value. On the other hand, if you choose a really high value of M, then what you're going to end up with is a flat line here on 0, which maybe comes up much later. And in that case, you're not going to end up with a very useful feature at all, because now you're just using the overall average for everything, and that will turn into a near 0 variance predictor. So this illustrates that trade-off, and this just shows how that would be calculated based on a given value of M. And then a couple of things in the blue box that are useful. We want to use this particularly, it's a little bit counterintuitive because we just talked about use cases in which high cardinality would be troublesome, right? A feature where there's a whole bunch of categories is going to be a problem, could be a problem for this if every single possible target value has a unique value, right? In which case, doing this kind of categorical combination isn't going to buy you anything anyway. But that's also the case in which high cardinality features are very difficult to fit by other methods. So a feature with a large number of categories can be very difficult to encode. You try to one-hot encode it, you're going to get a much higher dimensionality in your data set. So it's possible that target encoding is the most appropriate way to try to get some use out of this really high cardinality feature. And then also domain motivated features. It's always useful to keep domain expertise in mind. So here they show an example with a variety of zip codes, and we're going to look at movie ratings for a given zip code and see how they vary from one zip code to another. We're going to use the M estimate encoder, M equals 5. Here we are using the category encoders, which is from scikit-learn-contrib. And the M estimate encoder from that, you can actually encode multiple columns simultaneously, sort of like finding the interaction between columns here. But in this case, we're only going to pass the one column. So we fit and transform it, and then this is a visualization of the results. And this is the kind of thing that you want to see when you run this method. Here, the blue bars are the original data set. This is the distribution of the ratings. 4 apparently is the most common movie rating on, IMDb reviews. And what you want to see is that your feature computed by this target encoding M estimate has a distribution that is somewhere in between a spike at the overall dataset mean and the original distribution of the data. Keep in mind, if this distribution were to match the original distribution of the data, that would mean that you're overfitting. You're getting too much of the original values. the idea is to smooth it out, get a mean across a number of items in each class. So you want this to be a tighter distribution than the original.
Is the x-axis for the zip code line ratings, or is it zip code? I was confused a little bit here.
Is the x-axis, so it's rating, but it's a mean over all the ratings in a particular zip code. Yeah, it's a little confusing because they are both ratings. This one that's labeled rating is just the original data set distribution with no consideration of zip code. And this is the distribution of zip code mean ratings.
So each data point in the red line is what? Is the average rating in a specific zip code, or the average across multiple zip codes?
It's a kernel density estimate, isn't it?
I'm not sure I understood your question.
It's a KDE plot, right?
Oh, that one, yeah. This is a KDE plot of the
So I understand that from the rating perspective. I'm trying to understand it from the zip code perspective. I look at one data point in the red line.
Right. So
what does that really tell you?
What what this is doing here is there are so many different zip codes that we've just smoothed out the histogram with this kernel density method. So I'm not sure why the scales are different. I guess what you want for density is, I mean, these are the 5 possible movie ratings, right? So the distribution of this thing should sum up, these 5 fractions should sum up to 1.
Yeah, the KDE is basically
area under this, and the integral of the area under this curve should sum up to 1.
But rating is a discrete variable, right? It's not a continuous variable.
Yeah, and the KDE kind of fakes it being continuous.
Well, it's mean. Each measurement is the mean across a given zip code. So there could be, for a given zip code, there could be many reviews, and that mean rating is going to be a number somewhere in here. Right? That's why we have structure inside between the 3 and the 4.
Got it. Yeah, this was a confusing chart for me. Okay.
Yeah, what's confusing about it then is that when we get into the exercise, we'll see that the prediction, the original distribution and our target encoded get flipped, and there's a good reason for that. But I guess we'll jump over there now briefly. So we'll run these. Let's see. Couple of questions about choosing which features to run the encoding on, and here they're looking for the neighborhood feature, some of the features that have the most different categories, since those would be the toughest ones to encode by other means. And then you apply the M estimate encoding, and again we're looking at our housing price data set, and now we get another figure like this, but this time the KDE is the original data set, while the pink bars are the values in our target encoding. And the reason for that is that if we thought about the movie reviews, the original data set only had 5 possible values, while there were many, many zip codes, each of which could have their own mean. So it made sense to use the target encoding as the one with the KDE.
Mm-hmm.
But in this case, the home price is essentially a continuous value.
Sure.
So we have as many home prices possibly as there are samples in the data set. But there's a somewhat small number of neighborhoods, each of which has its own mean. So that's what we see down here on this density plot, is a pretty noisy looking histogram because there's only 20 neighborhoods or something.
So each bar represents a neighborhood then?
Each bar represents the mean in a given neighborhood, yeah.
Mm-hmm.
Or the median, I don't remember what it was we were encoding, but probably the mean. And then we run our score data set again at the end of this. And this was a really interesting example here.
Mm-hmm.
And this is where you start to see the problem where you could overfit target encodings. And we very briefly discussed at the beginning of that section how it's important to split. I don't even know if I mentioned it, but there was a brief discussion at the beginning of that last notebook how it's important, if you're going to train target encodings, you need to make that data set separated from your training data set for reasons that we'll see in this exercise down here. And this was really interesting that we fit to this data set and all of a sudden we get a ridiculously low number for your root mean square log error. And what I found interesting is it doesn't even matter what M is. And the reason for that is that we're using a gradient boosted model, and all that's doing by making M, even M as large as you want, it's still going to split the data set into these different discrete values. And because you're encoding the actual answer right there in the model, it's the gradient boosting regressor is going to be able to find that and pull that straight out. So this is showing how this method can lead to leakage that will compromise your model if you're not careful.
So you build a memorizer, right? Is that what you built?
Yep.
I was about to say that score is ridiculously low. There's a chart as well here somewhere.
Yeah, and this is how you see that it's a memorizer, is that it actually has the same distribution as the original data set. So the mean that is being used at each point is just 1 point.
Interesting.
And I just typed that up there, but so we've reached the end of the course. It's not been a short evening. There is a bonus lesson. I could touch on it very briefly. There's not much new. Bonus, that link apparently goes to IPython Notebook.
It's in the main page, the main.
Yeah, I'm trying to get the Zoom menu out of my way. Let's just pull this down. I think that's the one I want. It really just shows how one would chain all of the feature engineering steps that we've shown throughout this course into a single model. I'm not going to run all of this. The only thing I wanted to mention is there's one kind of new piece.
Didn't get the chance to run through this, so this looks interesting.
Yeah, the only thing that they mention here in this bonus notebook that is add-on to the material that was covered in the course is that rather than using a separate holdout set, completely separate holdout set to create your target encoding, you can actually get away with using a cross-validation trick, splitting the data into folds so that you don't have to throw away a quarter of your data just to train your target encoders. But that's shown how to do here. And then you get through this here, hyperparameter tuning. Train model, it shows you how to submit to this toy Kaggle competition. One thing that I thought was really interesting, if I can see which, I think it's here. So I made one submission to this thing, and somehow by just basically copying everything in that notebook, I think my submission is like already beating 80% of people, which is kind of surprising. You'd think that a lot of people would have run through and just copied that notebook in. But yeah, I think I'm here at 1,000 and there's something like 5,500 entries.
What is your score? 0.12?
0.12557.
12557.
And that's what you should get just copying that notebook, I believe. I don't think I made any substantive changes.
When we went over this data set in the original feature engineering course, I have a submission using Google Cloud Platform AutoML table model, and I have 0.12898, so a little bit higher than yours.
Okay, so maybe that notebook has a lot of people used that course and ended up up there.
Yeah, okay.
So what does that mean? That this is an upgrade on the original feature engineering course?
And then you're doing better than AutoML in Google Cloud, yes. Which tries to find the optimal model and the optimal parameters for you.
As you can see, I'm still a long way away from these
0.0?
perfect scores on the top of the leaderboard.
It doesn't sound right. Anything with too many zeros doesn't sound right.
Yeah, he's obviously played and figured out the test set. He's probed the test set for many months to get here or something.
What I find interesting is there are many people tied at this score, and
I think it's a public data set, so you can find the answers. Yeah.
Yeah.
So you're using a common data set, you're saying, David? They're using like a common third-party data set?
It's a public data set, so what I'm saying is he knows what's in the training data set, right? So now you know what's in the test data set. You know the exact answers. He just has to figure out the order. And
but usually they don't share the test set, right? It's not part of the.
This Ames data set, I believe, is fully public. It's not from Kaggle. It's not hidden, right? I mean, this is just their playground, right?
Yeah, it says getting started prediction competition.
It's like MNIST. You know, you'll see if you look at the one where for MNIST hand digitizing, right? You can go get it's a fully public data set. You can get all the answers and score perfect score.
Got it.
But it's, you're not learning anything. So what's the point?
So Robert, the notebook that you ran that had multiple features added to it, would the goal be to try different parameters or different feature engineering?
Yeah, and that was the idea. Was there were a lot of jump off points within that notebook, suggestions of ideas to try. There's a lot of room for exploration there.
Awesome.
I just ran it and submitted it once, but I didn't do any of that exploration.
I'll try the same and maybe try one or two options. Cool. Awesome.
Well, I think that's it.
Thank you, Robert. This was very, very useful.
Yeah.
Thank you for your detailed analysis and work and sharing it with us. Absolutely. There's a lot of traffic in the chat. Now is a good time to maybe ask some questions, get some feedback. But yeah, this is really a great session. Thank you everyone for sticking with us so late.
Yeah, if there's any questions in the chat, I haven't seen any of them.
Yeah, feel free to unmute yourselves. Okay, I'll stop recording here for our YouTube friends, and the floor is open for a little bit longer if you want to stay. Otherwise, we have to hop off. Thanks for joining us. This is a great session. Before I do that, before I stop the recording, let me just share real quick some upcoming sessions if you're joining us online. So this was the feature engineering one. We have 1 or 2 more sessions coming up. We have another one coming with reinforcement learning. This actually will be on some very basic heuristics that David and I will cover on this Halite simulation competition. For that, Alexandra and Dimitri will cover some notebooks on this Halite competition, the same one, and some other advanced techniques that competitors have used in this Kaggle competition. And Alexandra will share with us a little bit about this other competition called Hungry Geese, similar to Snake, of what does it look like, what approaches have people used, and just to get us familiar with the competition. So later on, hopefully we can revisit it. And then Robert will share with us version 2.0 of his presentation that uses now models to make prediction of when he goes to a bike share stand, will there be a bike for him, or will there be a place for him to return back his bike? If you missed the previous session that Robert hosted, it's on our YouTube page. Please make sure to watch it. It's right here, the last one. Cool, that's all I have in terms of content. I think there's one more, let me see, that we wanted to do before we go to our next adventure. That was I think the Tensorflow Summit. So we have a Tensorflow Everywhere Summit. This was held Feb 26, 27. It's about 4 hours each. There's 2 days, 8 hours of content. Feel free to look over it, and we'll talk about different topics that you might be interested in. There's many different topics, production related to using TensorFlow. So this was a very good summit. And that will wrap up all our Kaggle adventures, as well as some other branches that we've embarked on. And we have a happy hour here with a very simple notebook. I forgot to mention, this is a bonus lesson that the geospatial team and Kaggle added recently with tracking, I think, US vaccines in the US. So we'll do we've never done this happy hour plus one notebook combo, so we'll see how that goes. Cool, I'll stop sharing and I'll stop recording, and the floor is ours for however you want to stay. Maybe a couple more minutes. I know people are getting tired, so thanks everyone.